Hello, in this video we're going to look at power and sample size calculations for the multivariate sign test. Three background videos that I think would be worth watching prior to this are BV1, background video 1 is the sign test. I have a video that's titled that. BV2 is the multivariate sign test, and BV3 is using R, calculating probability for a bivariate normal random variable. We're going to go through each of these settings pretty quickly until we get to the power and sample size for multivariate sign test, because I covered it previously. So in this video we need the mass library because we're going to generate multivariate normal data. I think it's just easier to use a canned function versus creating it from scratch. This RM is remove variables and objects from the memory. So here's a quick example. Let's assume that the median vector is 0.5, 4 dimensions, 0.5 across, standard deviations of 2. We're going to assume this correlation matrix. I guess we could look at it if you want. And I just kind of picked those at random. Now from that, so given the standard deviation, the correlation matrix, then we can generate a variance covariance matrix from the the assumptions. Now let's assume we have a sample size of 20. We're going to generate data here. Since a sample size of 20 and we have dimensions 4, the structure of our data is 20 by 4. So each column is a random variable. And this is the sign test, these three functions. The S vector is a vector of univariate sign test. The V is sort of a covariance matrix associated with it. And the test is this. So it's 3 little lines to conduct the multivariate test. That in itself I think is so cool, so nice. And it's such a powerful test. Now we were in the alternative region here. You remember the null hypothesis is that the median vector is 0. And so we're in the alternative region. So one question might be, well, how large a sample size do I need to have, say, at least 80% power to detect that shift? And that's the next section of the videos. We're going to deal with that. Now, from BV3, we developed a function. So H here is actually the bivariate normal density, and so it's nothing new or nothing exciting there. But in BV3 we developed an R function to calculate probabilities in this bivariate normal setting, and that's what we're loading there, and we'll need that for when we do power and sample size. So here we're going to run through 3 examples, and essentially each example goes a little farther into the alternative region. And there it's just illustrating that you need a smaller sample size to detect a larger shift. So example 1, we're going to assume the median vector is 0.1 in 4 dimensions, standard deviation 1. We're going to assume that correlation matrix. Now we got to skip down to where we generate the variance covariance matrix. And then here, what is next is we're calculating the exact probabilities of the S, where that S vector is, the variance covariance matrix associated with it. And some of this is, I'm not going to go through it in great detail because we looked at it in the BV2, the multivariate sign test. But what I think is so fascinating, because we're going to assume that our underlying distribution is multivariate normal, these are exact calculations right here. So when we look at sample size and power and do simulations, they're exact calculations. Now, if the underlying distribution is not multivariate normal, then these calculations are asymptotically correct, and they can still be used for sample size and power calculations. So here, to find the sample size and power needed, first we assume a small sample size and calculate the power, and it's 0.05, which is not, we want, say, 80%. So what we do is we just create a while loop incrementing in by 1 each time, recalculate power, and do it until we achieve 80% power, and boom, it's done. So we need 702 observations to have at least 80% power. Now let's check this with a quick simulation. So we're going to do 10,000 replications using, the median vector is 0.1 standard deviations. That we're going to use the same assumptions. We're going to, generate multivariate normal data, 4 dimensions, and we're going to do 10,000 loops, and let's just see what the power should be. Or what we achieve, and it's 80.13, which is, exactly what it should be. Let's do example 2. Let's move a little farther into the alternative regions. Let's assume the median vector is 0.5, standard deviations are 2. I think we use the same correlation structure. Now let's generate the variance covariance matrix, and then here are the exact calculations for the S vector and the variance covariance associated with it. And now let's do a quick simulation. So let's generate the power and the sample size needed. 121 observations to achieve 80% power. Now let's kind of double check that with a simulation. And so we're again 10,000 reps, assuming that the median vector is 0.5, and we get 82% power, which is very consistent with what we should get theoretically. So in example 4, we're going to assume the median vector is 1, standard deviation 2. From those assumptions, we create the variance covariance matrix associated with that, and now we do exact calculations, and let's run a simulation to see if we're close. So we need 38 observations to have at least 80% power, and let's do a quick simulation to confirm that that's consistent with our theoretical calculations, and we get a power of 86%, which is consistent. Now let's create a power curve based on this last example. So the last example is the median vector is 1, standard deviations were 2. Here we just create empty slots, empty vectors to store our information as we go through the loop. So this while loop is exactly the same as the previous while loop, except for we're going to store the information, the n and the power that we achieve as we go along. And here, notice that I'd go up to 90% power because I want to see the whole range of possibilities. So let's plot it, and this is it. So this is the power curve associated with a median vector of 1, standard deviations 2, and this is sample size 38, where we went over at least 80% power. Now at 37, we were, say right here, we were just below 80% power, so we needed 38 to achieve it. Well, this is all I have for today. Hopefully you enjoyed that. I sure did. I think this is so cool that we can do some exact calculations for the multivariate sign test. Anyway, all right, well, like the video, subscribe so you don't miss the next one. Thanks, bye.